Welcome to today's webinar. I'm here in Colorado, and it's going to be a balmy 99 degrees today. So wherever you're calling in from, we appreciate you being here. Today's webinar is about the applications of artificial intelligence across wind energy science. And I am excited to be a part of the NREL's ongoing series of webinars called the Wind Energy Science Leadership Series. And these webinars have great success and robust discussions on wind energy related topics, featuring speakers from the lab, strategic partners, and even the energy industry. These webinars aim to address the challenges facing wind energy and the pathways forward for making wind one of the most prevalent energy sources of the future. So in today's webinar, you'll hear from a panel of NREL senior research scientists who will discuss how advances in artificial intelligence, machine learning, drive further progress in wind energy science and engineering. Before we begin, today's webinar will be recorded and available on demand on NREL's website and will be posted in roughly 2 to 3 weeks, so bear with us there. Again, please mute your phone lines and turn off your cameras if you're not speaking. We have a little bit of feedback in the background. And we also encourage you to use the chat feature or raise your hand to ask questions. And we will be answering those questions at the end of the session today. And finally, I would like to introduce Dr. Mike Robinson, Senior Technology Advisor and Chief Scientist for the Atmosphere to Electrons program at the Department of Energy's Wind Energy Technologies Office. Over to you, Mike.
Thanks, Alex. Good morning and welcome to today's presentation of the applications across wind energy science. You know, modern turbines are the largest rotating machines that have ever been produced by mankind. It has physical dimensions that are on the same order of magnitude as the atmospheric boundary layer in which the turbine operates. And of course, the wind turbine is just a single element in a highly complex and integrated wind plant system. These wind plants are comprised of multiple turbines. They're typically aligned in multiple rows, and each individual turbine is controlled to maximize the overall performance of the wind plant. And a modern wind plant is really a multi-scale and a multi-physics computational grand challenge. It requires high-performance computing on exascale computing architectures. In fact, some of the most recent computations that have been done at the National Laboratory have used 90% of the computational capability of the Summit computer at Oak Ridge. When you're trying to assess these performance of these wind plant systems onshore, your inflow driven by weather events, the terrain complexity, dynamics of soft rotating turbine systems, the production from multiple rotor wakes and the interaction of those wakes throughout the wind plant. Offshore, the CFD environment and the turbulence environment is even much worse. Turbines are mounted on floating platforms. You've got to consider the impacts of hydrodynamics, air-sea coupling, and the wake persistence in a stable marine boundary layer. All must for in your simulations. The future of wind technology will require really tools that will include resource forecasting, turbine design, development, deployment, and control. These new tools must have the same fidelity and physics that are typically included in high-performance computing models, but will need to run at computational speeds that support probabilistic design, closed-loop control of wind plant systems. The presentation today by Ryan and his colleagues will highlight the very first steps in developing these capabilities, utilizing both artificial intelligence, machine learning, and leaning towards edge computing for control systems. And so without further ado, Ryan, it's all yours.
Well, great. Thank you, Mike, for that introduction. We've got a lot to fit in today, so I'll jump right into it. So just to preface this, we've got 4 speakers lined up today, myself, Dylan Harrison Atlas, Mike Optis, and Ganesh Vijay Kumar. And what's kind of neat is that we're kind of reflecting a number of different centers across the lab, showing kind of the wide range of work going on in the lab around AI and ML applied to wind energy. And also a pretty diverse set of funding sources for this work from a number of different programs within the Department of Energy. So to jump right into this, the Biden administration's goals are 100% carbon-free electricity by 2035. And to achieve this pretty ambitious goal, we obviously need to massively accelerate our wind energy deployments. And here at the lab, we really see AI and ML as providing new pathways to improving processes around planning, design, and controls that can help achieve the administration's goals. Maybe just for a little bit of clarification around AI versus ML, we generally think of AI as kind of the science of making machines intelligent, and this is sort of the broadest category. And then as a subset of AI, machine learning would be giving computers the ability to learn from data without explicit instructions. So I'll often use these terms interchangeably, but just to avoid any confusion, ML will be a subset of AI. And as Mike alluded to, we're really seeing these emerging machine learning techniques as a new pathway that can encode insights and outputs from all the investments that we've made in high fidelity modeling and experimental campaigns, and make those insights accessible to tools that we would use for design, controls, and optimization. So yeah, in a little more detail, these high fidelity modeling codes are generally too expensive for situations where we need to run them repeatedly in these kind of outer loop applications. However, a lot of our existing reduced order modeling tools that we do use in these applications, really their inaccuracies become painfully obvious as we move to larger and larger turbines with nonlinear dynamics. So we're really kind of thinking about these machine learning tools as a way to make the insights from these high fidelity codes accessible at low cost. So you might also be wondering why the recent surge in machine learning. You know, this field has been around for decades now. And so what's new and where's all the hype coming from? And really the change is now this notion of depth in our machine learning models, where we're adding more and more layers to the networks. This leads to kind of better feature abstractions and more sophisticated algorithms and ultimately better predictive performance. These deeper networks have often millions of free parameters that need to be fit. So this actually plays in nicely with both the tremendous amount of data that has emerged recently and sort of this whole notion of big data, having these very large data sets to train these very deep networks. And then also hand in hand with that is the rise of GPU computing. These GPUs, as we'll show, are really key to being able to train these giant neural nets. And so you can kind of see what's happening with these deeper networks is that as you move deeper into the network, you can build up more complicated feature abstractions. So if it's an image classification problem, you go from pixel values to identifying edges to forming features, and this carries over into scientific applications as well, and ultimately improves the performance of our machine learning techniques. Also, across the DOE complex, in the last couple of years, DOE has made some pretty significant investments in scientific machine learning, basically applying machine learning techniques to scientific data sets as opposed to, say, natural images of dogs and cats. There's been a number of workshops led by DOE's Office of Science that identified priority research directions, and then those have been addressed in sort of a two-year sequence of FOAs in FY20 and 21 with almost $90 million worth of funding to tackle or to build a lot of these key scientific machine learning capabilities. And those are now starting to get incorporated into sort of the more applied program areas. So with that, the general layout for the seminar today is we have 4 case studies where we've applied AI/ML across the wind lifecycle. And this generally goes from largest spatial scales down to kind kind of blade scale. So we'll talk about resource assessment, wind plant surrogate models, some wind speed extrapolation and power curve work, and then finally with examples in blade aerodynamics and blade design. So the first case study is looking at super resolving wind data in different future climate scenarios. So the general setup of this study was, we wanted to be able to say something about how different climate scenarios might impact different development and deployment strategies for renewable energy. When we take a look at the global climate models, their output is almost necessarily coarse, just so that you can run these models over many decades and at global scales. The spatial resolution of global climate models is typically about 100 kilometers. However, we know from experience at NREL that we want spatial resolutions closer to 2 kilometers to make it accurate wind resource assessments. So kind of the natural question here was, can these emerging scientific machine learning techniques help bridge this scale and perform this downscaling? So in the natural images side of the machine learning field, there's a technique called generative adversarial networks that has been very, very effective on super resolving images of everyday objects. And the machine learning community often uses the term super resolution, but it's essentially the same thing as downscaling, which might be more common in an atmospheric science community. And this GANs, or this general adversarial networks approach, has been really quite powerful and really, really advanced the state of the art in machine learning. The general idea of what's going on with this approach is you're training two competing neural networks, kind of indicated by these two colored boxes. One is called the generator, one's called the discriminator. In our implementation, these are convolutional neural networks, which is a network architecture that's really well suited to images or field data, such as wind velocity fields. The generator network here is trying to learn to produce sample images that are consistent with the distribution of data in your training data set. And it's also trying to fool a discriminator whose job is to distinguish between sort of real and fake images. So you can almost think of this as generators trying to print counterfeit money, and the discriminator is trying to identify real bills and fake bills. And when we're training these machine learning models, these networks are actually competing against each other with this min-max objective function. And as the networks get better and better over time, you wind up with a generator that can produce very compelling images and a discriminator that's very good at parsing out real versus fake images, and basically learns to identify if the physics represented in, say, your wind velocity fields are correct or not. So we applied this approach on a number of NREL data sets. So the goal here was to be able to enhance the resolution of data coming out of NCAR's CCSM model. This is a global climate model, and it's the one that's used in the IPCC studies about global climate change. So this is kind of the de facto computational model when thinking about climate change scenarios. To train the model, we need both low resolution data and corresponding high resolution data. So what we've actually done here is started with NREL's Wind Toolkit. So this is high resolution wind data that came from WRF, so a weather prediction model. And this has data at our desired high resolution, and we've coarsened it to low resolution that is equivalent to what's in the CCSM model. So the first step is training our GANs network to learn this mapping from low resolution data to high resolution, where we have a ground truth and can train the model. After it's been trained, we then turn around and apply it to outputs from NCAR's CCSM model. And we've done this on wind and solar data, but I'll primarily here focus on just the wind data outputs. So here's an example of some of the outputs from this GANs model. These are 1,000 kilometer by 1,000 kilometer slices, just sort of randomly selected from around the globe. The two rows here I'm showing are two different wind velocity components. And this is a slice taken at 100 meters as sort of a nominal hub height. First column on the left is the low resolution inputs. And then we show a number of different ways that you might do this downscaling. So the first is just sort of a naive interpolation. If you didn't want to use any machine learning techniques, you can see it's still unrealistically smooth. The middle column is if you just had a convolutional net, you can see it's improved, or we are picking up on some sharper features of this one front, but definitely still lacks a lot of the small scale information. So an improvement on that is to bring in this whole notion of adversarial training and have these networks competing. So the GAN's output is this fourth column, and you can see this does capture a lot more of the right sort of small scale information. You can almost think of this as almost texture in the image, but it's really more physically meaningful than just that. And then comparing against the ground truth that we did have in this case. So when we trained this model, it took us about 3 days on one GPU to train this, but the computational cost is very asymmetric. So training is orders of magnitude more expensive than evaluation, and we're actually able to generate each of these slices in less than a second. So all the computational cost is front-loaded. We had a PNAS paper last summer that came out that spent a lot of time looking at quantifying the performance of these turbulent flow fields and looking at how realistic is the output from this GANs model. And we were really pleased with the performance here. We're able to capture almost an additional decade of inertial range, kind of building out the correct energy spectra with the GANs model. We're even getting the velocity gradient PDFs correct, including negative skewness. I'm also showing some results here on the solar data, but that's equally impressive, but maybe not quite as relevant to the wind energy community. And yeah, we really attribute a lot of this improved performance on these sort of turbulent flow characteristics to this adversarial training. So when we added in the adversarial training piece, you can see on these curves the point-wise errors actually suffered a little bit, but in general, we saw much more realistic flow fields in terms of obeying turbulent flow physics. And what's really remarkable is that the machine learning model, didn't know anything about Kolmogorov turbulent kinetic energy spectras or anything like that. It's really the discriminator learning to identify the right physics and then encoding that into the generator. So we're also able to run this model globally, which is pretty exciting. So here I'm showing outputs from our global super resolution and then zooming in just on a few places. And you can see the kind of characteristics of the super resolved fields that exist on this global data set. And we're able to generate these globally super resolved outputs in about a minute. So kind of wrapping up that part, we developed a network that does 50x resolution enhancement of wind data and 25x resolution enhancement for solar. This network is, we've released this open source on GitHub. You can find the code here. It's fully trained, and there's some example data to stand up a demo of your own. And then there was this PNAS paper last summer as well. And this goes into much more detail about the network architecture, the training process, and a lot more about the kind of turbulent flow analysis. And then there's just 3 other quick extensions I wanted to touch on. So first off, we've developed analogous networks for a number of other atmospheric variables. So obviously, if we care about wind power, we need more than just wind speed. We need to say something about air density. So we've developed this for temperature, pressure, and humidity, everything that you would need to compute an air density. We're also doing some studies now to look at hybrid power plants by using sort of concurrent wind and solar data sets that have been super resolved and are able to capture changes in the correlations between wind and solar resources during these different climate scenarios. We've also extended the network to do both a spatial and a temporal super resolution. And so specifically, we have a network that does a 10x spatial enhancement and a 24x temporal enhancement. So here's an example of what that looks like. So you can see one of the velocity components, the low resolution on the left, which is at daily intervals. And then our GANs output has been super resolved to hourly intervals. And we're comparing against just a naive interpolation. And what's really neat here is that if you just interpolate, the storm front just kind of pulses in and out in place. Whereas with our method, we're actually able to capture advection as this front moves through the domain. And what that translates to for the wind community is basically we're able to capture correct ramp rates. So for grid integration studies, this is really a key notion. And then finally, we're also interested in being able to produce multiple realizations of these super resolved outputs. So we can do things like studying extreme events, looking at uncertainty quantification. So we've further modified our network to include what we're calling a diversity term. So now we're producing batches of super resolved fields. And this diversity term basically encourages these images to be different from each other, but different in a way that's physically realistic. So when we look at the spatial statistics of these ensembles, they have the correct higher order moments. And so this is under review right now in JCP, and we'll be making this open source as well. So I'll wrap it up there. Again, we have this 50x spatial enhancement tool that's been open sourced. We can run this on arbitrary size data, so whether it's these smaller 1,000 kilometer by 1,000 kilometer slices all the way up to global data sets. We have the capability to enhance resolution both spatially and temporally, and we can produce multiple super resolved realizations, so enabling sort of probabilistic studies. And with that, I think we'll transition to our next speaker. Dylan, I will turn it over to you.
Great, thanks, Ryan. Appreciate it. I'm Dylan Harrison-Atlas. I'm a researcher at the National Renewable Energy Laboratory. My work focuses on national assessment of renewable energy problems and solutions using geospatial and machine learning methods. And so today we'll talk about an application for wind power using surrogate modeling. In the United States, wind power currently accounts for 8% of domestic energy production, but this number could rise to 35% or higher by 2050. So with that type of growth, wind power is increasingly seen as a key enabling technology for sustainable energy. And with that magnitude of growth, it becomes increasingly important to develop national perspectives around wind power and the role that it can play in advancing an energy transition. In particular, national perspectives are needed to help us prioritize different investment strategies, to help us understand what are the broader collective impacts of such large-scale deployment on the landscape, and also what is the role of different technology innovations that could help us advance and meet our complex sustainability goals. Of course, the challenge with informing this national perspective is that with wind power, outcomes, including plant performance and other sustainability considerations, depend on localized factors like wind resources, as well as technology that continues to evolve and drive possibilities. And so how do we bring this all together in a way that can help us understand this bigger picture? Well, in this regard, we think that AI can help. Specifically by providing tools that can capably evaluate and help us explore this complex and dynamic space. So today we're hearing about a diverse set of opportunities for AI in wind power. One of the key opportunities is at the heart of this persistent trade-off that we find in the wind energy modeling community, and that's between model fidelity and model scalability. The models that are higher fidelity that can generate these really rich insights at high resolution tend to be relatively unscalable due to their computational demands. This is a challenge because existing models are tailored around narrowly defined use cases or applications. So even if we have a model that works really well for a specific case, we can't just apply that for thousands of locations across the country and for a wide range of conditions or design considerations, for example. And so really what we need are methods that can balance fidelity with scalability, as Ryan alluded to in the introduction. And so in this context, AI surrogate models may offer a path forward where we can leverage those insights from higher fidelity models without sacrificing scalability to help us inform this national perspective that, again, is really all about how do we identify opportunities that exist at the intersection of this design and geographic space as the two come together in interactive form, potential futures of wind power. So when we talk about surrogate modeling, it's helpful to think about the alternative or the traditional way of modeling for wind power. In this context, we typically would have our model, which we're calling here a full form model. And we would feed that input data as well as information about the design of a wind plant layout or turbine characteristics. And that information would go through a model and would give us an outcome that we're interested in. The challenge here is that oftentimes these processes are computationally intensive and they can pose a bottleneck. So we're interested in those outcomes, but we're maybe less so in how we got there. And so this is where surrogate modeling comes in. So in this case, surrogate model is essentially its approximation that allows us to efficiently go from our inputs to our outputs in a way that's streamlined and efficient. You can advance, Ryan. So the goal of the work that I'm presenting this morning is to develop a streamlined surrogate model for scalable assessment of wind power. In this case, we're focusing on a graph neural network as the basis for a model. And really what we're doing here is looking for opportunities to develop streamlined access to the insights that the full form model is giving us. In this case, Flores is an open source model developed by the NREL community that we're using as our full form model. So to do this, we represent the wind plant as a graph. The graph consists of nodes and edges. Nodes are the turbines, edges encode interactions or potential wake effects between downwind turbines within our graph. So the graph neural network is composed of a set of GraphNet blocks, and these propagate information throughout our graph structure using a series of update and aggregate functions. And importantly, this graph structure, it's been infrequently applied in the wind space, though I suspect that will be changing in the near future. But it's quite flexible for this type of problem. It can scale up well, and it can also provide insights both at the turbine or node level, as well as looking at interactions between turbines and also at the plant level. So one of the challenges with AI and machine learning is that models are typically only as good as the data they're trained on, and this application is no exception here. And so one of the limitations that we identified is that in the real world, there are only a finite number of existing wind plants in operation. And so we wanted to extend the ability of the model to learn about plant performance for layouts that don't currently exist. But this can be challenging to generate realistic plant layouts. But we developed a tool to do just that. We've based off Denholm's earlier work that classified 4 canonical layout types of plants that are commonly found across the US. We developed a tool to be able to generate random realizations of these different archetype layouts and for a variety of turbines. So for each of those layout types, we were able to randomly generate a feasible wind plant layout ranging between 25 and 200 turbines. So looking at a wide variety of potential layout configurations. In addition, we wanted to understand how various atmospheric conditions would relate to plant performance. And so we captured those according to wind speed, direction, and different levels of turbulence intensity. In addition, we also wanted to capture the effects of turbine level controls on plant performance. And so we introduced yaw angles as a variable within our model. So in total, we conducted, actually go back real quick, Ron. In total, we conducted over 250,000 simulations where we fed this information through Flores and recorded the outputs. The outputs were recorded both at the turbine level and the plant level. And then we withheld 5% of the simulations so that we could assess how well does the model do when we try to generalize it to conditions and layouts that it's never seen before. So when we confront our model against data that it's never seen in this test set, we get really exceptional performance as indicated by this table here in the top. So these are for wind plants in conditions that it has not seen before. So at the turbine level and the plant level, the errors are quite impressive, generally on the order of 1 to 2% maximum. And the animation on the lower left shows here for one of these example wind plants layouts that's from the test set, how the model is able to predict turbine level power output as we rotate through inflow directions. And so we can see that the model predictions closely track the directionality of the inflow, and that the errors shown in the graph on the right are relatively low. At the bottom, the model is able to capture aggregate plant output, and importantly, it's able to reduce this characteristic behavior that we would expect, when the inflow direction aligns with the rows of turbines, we see this characteristic drop in power. So this is good behavior. In addition, one of the key aspects of the surrogate model is that it's able to rapidly evaluate plant performance, not just for a whole variety of potential plant outputs or plant layouts and configurations, but also for a comprehensive set of inflow conditions. And so we can take our model and develop a response surface that we show here in the upper right, which shows for every combination of inflow, wind speed, and direction, what the predicted power is. And we get a sense for how good those predictions are, at least compared to our ground truth Flores model, by comparing them against that similar response surface obtained from Flores. So that's shown on the bottom. Again, the errors of this relative to the scale of this particular plant are quite small, in the order of 1 to 2%. One of the key motivations for developing a streamlined surrogate model was so that we could evaluate technology, innovation, benefits, impacts at scale. And so one of the key innovations that's on the horizon is wake steering. Ryan, can you just hit the button once? So for those of you who are not familiar with wake steering, this refers to the practice of intentionally misaligning a turbine rotor with incoming wind in order to reduce waking for downwind turbines. The effect of wake steering can be to increase plant power output, but there could be other benefits as well, including enabling greater siting flexibility through denser turbine layouts. The challenge with wake steering is that methods for doing so, at least conventionally, are really costly due to the optimizations that are involved, especially for large farms. And so we needed a streamlined, efficient method to be able to give us those insights without having to sacrifice the scalability. So in practice, this is what wake steering looks like. This is just for the toy example wind plant here. We've got 5 turbines. In the upper right, we show that the wind in this case is coming right to left. And the model is able, through this optimization, is able to determine the optimal yaw angles for each of those turbines with respect to the inflow direction. Interestingly, the model is able to capture this behavior where individual turbines might sacrifice their power output, but just to improve the plant level power output. And so this is a good outcome that we would expect to see, and the model is able to do this really quickly and efficiently because it has automatic differentiation capabilities that runs quite fast. And so this is important because it enables us to scale up this type of approach for larger scale assessments. The reason that I keep coming back to national scale assessments as being important is because increasingly there's discussion and consideration of ambitious clean energy goals where wind power plays a prominent role in that transition. And so this animation that we're seeing here shows for a 95% decarbonization scenario by 2050 projected build out for wind power in the US. And this visualization, I think, really gives a sense for the magnitude of deployments and potential landscape interactions that we might expect for wind power in the coming decades. So in total, this scenario here represents 720 gigawatts of onshore wind power at nearly 7,000 build-out locations. And so we were interested in understanding how can we apply our surrogate methods to understand opportunities for technology innovation at this scale of deployment. Can you go forward one slide, Ryan? I think we lost Ryan. Let's give Ryan a second to see if he can connect back in.
You want me to share the slides so that you can keep going?
Yeah, if you have them up, that would be helpful. Otherwise, I can pull them up.
Oops, sorry, that was the wrong one. I believe you're here.
Yes, perfect. Awesome, thank you. And so we were interested in, for that scale deployment that we visualized in that animation, trying to understand, again, how could technology innovation play a role in potentially minimizing some of the impacts of that. In particular, with wind power, there are a number of sustainability implications associated with its footprint. These vary along social, ecological, and economic dimensions. And for all those reasons, there could be interest in minimizing the footprint of wind power, both at the site level, but also more cumulatively at the national scale and across ecosystems or ecoregions. Again, using traditional methods to do this type of optimization can be intractable, particularly for a broad range of design considerations. And so this was an opportunity for us to demonstrate the efficacy of the surrogate model. So this animation shows here an example optimization for one of those 7,000 build-out locations. What we do here is we account for the local wind resources as well as land availability at each of those projected build-out sites. And then we apply a series of spatial optimization iterations to essentially compact the footprint of wind power as much as we can without sacrificing the annual energy production from that particular wind plant. And so that's demonstrated here with this animation. We're able to effectively do that both using wake steering, which again is a function of the optimization, as well as doing it without any type of wake steering, so we can evaluate the benefit from that particular innovation. Next slide. So when we applied that method to all 7,000 of those build-out locations, we see that there are considerable benefits of wake steering, at least in terms of reducing this cumulative footprint. Roughly on the order of 10,000 square kilometers of land sparing are possible through these denser turbine layouts that are again enabled by wake steering technology. For some plants, these footprint reductions are even larger, upwards of 50% or even greater. And wake steering can increase energy yield. So this is important as we look to maximally harvest energy per unit area. This can help us reduce critical interfaces with social and ecological systems with wind power. And it can also create new opportunities for geographic deployment of wind power, particularly in regions that historically have had land constraints. So in conclusion, our method enables rapid and sweeping study of technology innovations, as well as wind plant design scenarios. And more broadly, AI surrogate approaches are able to balance fidelity and scalability in ways that were not tractable using conventional methods. This is critically important as we look to provide big picture assessments of renewable energy to support a clean energy transition. Thank you.
Great. Let's see if Ryan's back. If not, we can bring it.
Sorry about that. I had VPN issues. I can pull back up the slides here. Okay, Mike, over to you.
Great, thanks, Ryan. So I'm Mike Optis. I'm an atmospheric and data scientist here at NREL, and I'm going to take a little step back and talk a little more about simpler machine learning for a range of common wind energy applications. Next slide, please. So I think maybe based on the first two talks and generally, I think in the community, machine learning can look and sound overwhelming a lot of the times. We've already talked about deep learning, convolutional neural networks, general adversarial networks, surrogate modeling, and things like that, which are totally appropriate for the applications that Ryan and Dylan illustrated. But I think it's important to remember that machine learning technically applies to linear regression too. You know, this is an algorithm that we don't have to, that's kind of automated. It gets better with more data. And technically, it's the simplest of a machine learning model, but technically is machine learning. You can see on the right here, more data, less uncertainty, and a line of best fit. Of course, machine learning today, when we talk about it, it generally refers to more complex statistical algorithms, and particularly those that can reveal relationships between variables with less imposed constraints or little to no imposed constraints. Whereas, you know, linear regression assumes a straight line. Machine learning, modern machine learning algorithms are particularly good at identifying nonlinear relationships without those types of constraints. Next slide, please. So I tend to operate in what I call the machine learning middle ground for many wind energy applications. And this is possible because in general, wind energy applications don't have that much data, you know, relative to the millions and billions of data points we might see being tackled by a deep learning network, for example. We tend to operate with time series data, wind power from a wind farm, maybe multiple atmospheric variables. And in general, these data are pretty small compared to other much larger big data sets. And also they usually only have one predictant. You know, if we're looking at wind power output from a wind farm as it depends on measured atmospheric variables, we're only interested in one variable, which is wind power. Or if we want to extrapolate winds up to hub height, we're only interested in that hub height wind. So this kind of simplifies things in a lot of cases. And to that aim, we've had a lot of success with pretty simple ensemble-based regression trees. And these are, you know, things like random forests, gradient boosting, extremely randomized trees, and things like that. And on the right is a very basic idea of what a regression tree looks like. So if we had a bunch of test scores, for example, and the average was 2.5, if that was our prediction for each data set, there'd be a large amount of error because, you know, they range across the average. But if we found ways to split that data, say based on male and female, we see that male or females score almost twice as high in this case as males. And then if we then applied that to our prediction, if it's a male scores this, if a female scores this, we get a lower overall error in our model. And this kind of continues down and down into multiple layers of branches, as they're called. In this case, we're looking at previous homework scores, and the data gets even better. So this is the idea for a decision or a regression tree. We tend, when they get more variables and a much larger data, we tend to use ensemble-based approaches where we tweak things in the tree and run it, you know, thousands to tens of thousands of times to improve predictions. But this is the basic idea, and it's proven very successful for several wind energy applications. And I'll just touch on a couple of those in this presentation. So first is wind speed extrapolation. We do this all the time in wind energy, whether we have a 60-meter Met tower onshore and we want to scale up to hub height, or we have weather stations, satellite measured winds on the ocean, or buoy data. And there's always this need to extrapolate winds near the surface, not just a hub height, but across the entire rotor swept blades, especially as we have wind turbines extending, blade tips extending almost to 300 meters above the ground level, in the next decade or so. And in general, we tend to use these very simplified extrapolation models, things like the log law, power law, which are heavily constrained, and also break down, especially in conditions of stable stratification, or if we see low-level jets, et cetera. These models do well if we're talking about a mean average, maybe over a year of data. But as we increasingly become interested in time series data, these models quickly break down, and we really have an opportunity to find better extrapolation methods that aren't bound to these very specific constraints of these simplified power extrapolation models. So to that end, we've have a lot of success using random forests and gradient boosting for wind speed extrapolation. So there's a couple papers for an onshore and an offshore case I've kind of highlighted below. But the basic idea is we take relevant parameters at the surface, things like wind speed, wind direction, air temperature, and in the offshore case, sea surface temperature, and then we train a ensemble-based regression tree to predict the winds at hub height. Pretty simple, completely statistical. We're not assuming any sort of physics here, but we're also not bound by any oversimplified physics assumptions, such as the log or power law. So just quickly, one slide on results here. I'm only showing the mean wind profiles. We have a lot more time series based performance metrics, but we found compared to things like the WRF model, typical log profile, and even a more physically appropriate single column model, we see the line in blue on average at these two LiDAR locations off the Atlantic coast show extremely strong agreement with observations. The observations are the darted black there. And this is pretty promising. This holds across different stability regimes. The diurnal cycle looks really well. It can even predict low-level jets, again, based entirely on a statistical approach to modeling the wind profile. So the last example I want to talk about are wind plant power curves. These are being used increasingly more for operational energy assessments, whether we're trying to assess plant performance or we're getting ready to buy or sell a wind farm, figuring out how the wind farm performs relative maybe to its pre-construction estimate is a really important thing. And in general, when we try to run physical models, we struggle with the uncertainty associated with wake losses and how the winds move the wind farm and all that. Alternatively, statistical models can be really powerful, whereas wind speed, for example, would be an obvious parameter controlling wind farm output, but also things like wind direction and stability. And as we add more of those features, we can reveal the importance of multiple atmospheric variables in building a strong wind plant power curve. So on the right, we see if we were to draw a line of best fit, this is using a generalized additive model, there's a lot of spread in a simple daily average wind speed versus daily gross energy from the wind farm. And we can do a lot better if we start looking at more atmospheric variables in what we can consider a multidimensional power curve. So what we found here, apologies for the abbreviations, but in the bottom right legend, we start with wind speed in blue and we consistently add more and more observations from this sample wind farm. So wind direction, pressure, temperature, TI, wind shear, potential temperature gradient, turbulent kinetic energy, and the Opogov length. And here is just one plot showing the diurnal cycles, again, using 5 different machine learning models. So a neural network compared to a GAM and a couple of these ensemble-based regression trees that I showed, as well as a support vector machine. And in general, if we just look at some of the ensemble-based trees, like say the gradient boosting model, we see that as we add more of these important atmospheric variables, the agreement with the average diurnal power cycle to observations becomes stronger and stronger. So we're gaining a lot of skill by considering these additional parameters. And in fact, what we found is that after wind speed, turbulent kinetic energy is the most strongest predictor of wind plant performance, even ahead of wind direction, which was a nice result. Oh, sorry, an animation snuck in there. So maybe hit the slide once, Ryan, just to reveal that animation. Thanks. So finally, this is again looking at the importance of variables versus the algorithm. So I'm showing the normalized root mean squared error in power production. On the y-axis, we have our 5 algorithms. And again, on the x-axis, we have the situation where we start with wind speed and consistently add additional parameters. And what's interesting is if you look from top to bottom, things don't seem to change that much for this. You know, we don't get significantly better results using a support vector machine versus a neural network, for example. And that points again to this idea that with these small data sets, we don't really need these complex algorithms. Instead, what's really important are the variables. And if you go left to right, we are consistently going from red to blue, indicating better and better results as we add these important variables. So I think it's critical in these type of applications that let's not focus on a deep learning neural network if we're just going to feed it wind speed data. Let's simplify the algorithm and make sure we feed the model the right data to produce better results. So in conclusion, we've done this with a lot of other use cases at NREL. Again, the power of these simplified machine learning models is pretty impressive, but time is short here, so I can't speak to all of them. But I think machine learning, it can sound complicated and inaccessible, but I think it really isn't. And I really wish we just called it statistical learning, because that's essentially what it is. I think the machine is a bit of a buzzword, but that's where we're at with it. But we found over the last few years that relatively simple algorithms are perfectly adequate for use across a large range of wind energy applications and provide much better results than some of these simplified physical models. And finally, this is pretty accessible given that modern programming libraries like scikit-learn and Python are really making this easier than ever to use. It's not as simple as plug and play or black box. That there's definitely best practices involved in how you train your model and the data that you use, but it's getting more and more accessible, and that's pretty exciting. So yeah, thanks for your time.
Great. Thanks, Mike. Ganesh is up next. So Ganesh, I'll turn it over to you.
Thanks, Ryan. My name is Ganesh. I'm a researcher at the National Wind Technology Center with a background primarily in computational fluid dynamics applied to wind energy aerodynamics. And off late, I've been trying to understand how to translate data from a lot of this stuff into design. So with that, I'll be focusing my talk on improvement of aerodynamic models using machine learning and high fidelity modeling. So the crux of the problem here is that some of the current aerodynamic models that are used in rotor design and optimization are hitting upon the limits of simplifying assumptions and the corrections, the empirical corrections to those assumptions. A lot of the current design techniques use something called blade element momentum theory, where they assume a very simplified uniform inflow with an assumed wake shape and so on. So with that, so advance please. So some of the corrections to the limitations in these models are hitting against their limits, and this is going to prevent us from designing wind turbines of the future, which are going to be experiencing a lot more complex effects like unsteady aerodynamics around the floating platform motion, large shear and wear where the sizes of these rotors are increasing a lot. So in order to achieve this, what our proposed path forward is actually augmenting the aerodynamic models that exist for design and optimization using deep learning neural networks. So similar to a lot of the talks shown earlier, the goal here is to actually have a surrogate model that translates information from a lot of the geometry and other information that dictates the design and the inflow conditions into aerodynamic performance like lift, drag, power, thrust, etc. And not just that, sometimes you also want to be able to go back and use it in a design framework where you want to apply a specified performance and get the shape that actually matches that the best. So in order to do this, a lot of this neural networks will be trained using experimental and high fidelity simulation data that have been validated against other experiments in the past. So what I'll do here in this talk is provide 2 examples of this design high fidelity modeling to design pipeline. So the first of it is going to be focused on unsteady aerodynamics modeling, and the second one on the inverse design of airfoils and wind turbines. So I'm going to be presenting some results here on unsteady aerodynamics modeling that have primarily been published in these 2 papers. I would like to thank my colleagues here, Shreyas, Shashank, and Emmanuel, with whom, without whom this work would not have been possible. So moving to the next slide, the main problem that we're trying to address here is this. So there is a significant portion of the future turbine blades are going to be experiencing major unsteady aerodynamics effects. This is shown by a picture of a current generation blade from the Grand Challenges paper that was discussed earlier. So this shows a blade that is actually pretty thick near the root and actually kind of thins out as you go towards the tip. And future blades are going to be even more so like that, along with a lot of increased flexibility. These turbine blades operate under turbulent inflow conditions where there is a mean shear across the entire rotor disc, as well as a lot of turbulent inflow that changes the velocity field around it. A lot of this ends up in creating unsteady loadings and inflow conditions on particular sections of these turbines called airfoils. So the plot on the right shows a measure of the unsteadiness over the blade length at around three times per revolution forcing for 4 open source wind turbines available in the literature. So what the measure of this reduced frequency is a measure of this unsteadiness. And when that number is under 0.05, you have basically quasi-steady aerodynamics effects, where when that number extends above 0.2, you end up with major unsteady aerodynamic effects. So a lot of the current models do not completely capture the effect of all the unsteady aerodynamics very accurately. So the goal here is to actually improve some of these unsteady aerodynamics models. So this accurate prediction of these unsteady aerodynamics is necessary to predict the fatigue life of these turbines. Many of the current turbines are designed to actually operate over a 20-year lifespan to be commercially viable. In order to do that, we need to understand the full picture that goes from what happens when you have unsteady inflow all the way down to the plot shown on the bottom right that actually results in unsteady loadings. The plot shown there is a measure of a lift coefficient against the angle of attack experienced by a particular section on this blade. And the green line shows the mean response, whereas the orange and the blue lines show what the response will be if the flow is unsteady. So this ends up resulting in a large blade deflections that basically contribute towards fatigue along with the corresponding loads. So in order to do this, predict this information, so what we do is develop a deep neural network surrogate for the unsteady aerodynamics response. So the goal here is to represent the deviations in the lift coefficient and the drag coefficient and other quantities of interest from their mean quantities. And we do that based on understanding the physics, which is where we know that the main things that contribute towards that response are the rate of change of angle of attack, and their higher derivatives, along with other things like the airfoil shape and the Reynolds number. So the particular network of interest here, if you advance the slide, is the long short-term memory networks that are a type of recurrent neural network that is able to predict the evolution of these quantities over time. So it understands a bit of the hysteresis by understanding a bit of the time history of the quantities of interest in the inputs described earlier. So let's see how this model performs. The machine learning model we show that it captures both the lift and moment response much better than the state-of-the-art models like the Beddoes-Leishman model, the Martin-Hansen model, and OA model, and so on. These results have been discussed extensively in the papers described earlier. And what I'm showing here is just a sample lift and pitching moment response for the N415 airfoil that was measured in the Ohio State wind tunnel experiments. The lines in the gray show the experimental results, which are also, as you can see, they're not repetitive. So they have slight variations from cycle to cycle. And our machine learning model is able to capture both the overall hysteresis loop as well as some representative cycle to cycle variations, which are very, very important in terms of fatigue loads. And not just that, we also are able to capture the moment response as well, in addition to the lift response. And this is very critical for highly flexible bend twist coupled blades of the future, where any kind of bending is going to come along with a lot of twisting. So we have integrated this tool into OpenFast, which is the whole turbine simulation tool from NREL, and this allows for direct use in design load cases to help improve designs of the future. Moving ahead, so I'm going to be describing some of our work on the Integrate project that is funded by the ARPA-E program under the Differentiate FOA. This work has been in collaboration with some researchers from the University of Maryland and a lot of other people who have been providing computational fluid dynamics expertise, along with a lot of the machine learning expertise and the relevant area expertise at NREL. So
Ganesh, we are at the end of the hour, so we should just try to hustle through these as best as we can.
Okay. So moving to the next slide. So the main goal here is to perform an inverse design of airfoils and wind turbines using high fidelity nonlinear aerodynamics. So simply put, the goal is to go back as compared to typical surrogate models where they go from design to performance. But the goal here is to go get the designs for desired performances on your laptop in under 1 second. So the AI enhanced CFD workflow actually provides the training data, and this enables an innovation in the turbine design itself by allowing for up to a 5% reduction in their cost of energy through an integrated airfoil and blade shape design. So this also helps improve accelerate the time to market with more certainty in the early design iterations, as well as search through more designs through improved performance and robustness. So moving ahead, so this is our airfoil design methodology that includes both the aerodynamic performance requirements in terms of aerodynamic quantities of interest, where we want drags less than a certain value and liftover drags more than a certain value, and etc., as well as structural considerations like maximum thickness. So as you can see, the max thickness varies along the blade, and we want to be able to design airfoils at all sections of the blade. To do this, what we did, moving to the next slide. We've developed an automated CFD solver pipeline for generation of this training data, where we show the ML model all kinds of performances for the airfoils around perturbations to a lot of the baseline shapes. So the middle figure on the left basically shows one baseline airfoil that is known to be relevant to wind energy applications and a lot of perturbations around it. And when you do this for a significant number of baseline airfoils, you cover the relevant design space on the left shown here. And the automated CFD process, HAM2D, developed at the University of Maryland, allows us to translate the effect of all of those things into the design quantities of interest, which is lift, drag, and other quantities of interest. So using this training data, we have demonstrated the success of this method of using sparse neural networks for inverse design of airfoils by having a specified aerodynamic performance requirements as shown on the right. And that results in, we developed 100 shapes that satisfy this criteria, and we have verified that all 100 shapes basically satisfy this. This paper is under review at an AIAA journal here, and this shows how one example of those designs where it predicts not only the airfoil shape, but also the operating point of the airfoil, where the angle of attack is chosen such that it matches these criteria. So moving ahead, so the ongoing work right now is to we have successfully demonstrated the success of this invertible neural network approach for airfoil design, and we are moving on to full 3D blade design using invertible neural networks, where the number of parameters used to design this turbine really explodes compared to the 2D airfoils. We are also pursuing an integration of this airfoil design strategy into Wisdom. So this will allow for multidisciplinary optimization of wind turbines as well. So the main conclusion here is AI and ML provides basically a very novel pathway to bridge the computational complexity of the high fidelity and high performance computing environments, along with design and optimization needs that basically need to be running on laptops, workstations, and cloud computing platforms. The key to this is getting the right kind of data from validated high fidelity modeling combined with experimental data to use in design and optimization techniques. Thank you.
All right. Thanks, Ganesh. I think I want to get to some questions in the chat, so I'll maybe just leave some of these parting thoughts up here. And I know we had questions come in on the chat, and if people want to raise their hand for questions as well, I think, we're definitely interested in engaging with you guys. Okay, I'll do my best to kind of MC this Q&A. Maybe, let me see here. Looks like we had a question from Basu, hypothetical scenario, suppose that the course resolution wind field shows a wind ramp event occurring near Colorado. Okay, so I think the question here is basically about timing of the wind ramp events using super resolution. And if there's a disagreement between the course data and the high resolution data. So one point to clarify is when we're super resolving the climate data, there is no ground truth. So we don't necessarily have that disagreement scenario. The GANS data also, it only produces one of many plausible realizations. So I think about it as a sampling tool that's sampling from high dimensional distributions of possible super resolved high resolution data. And so there's actually many solutions of high resolution data that when coarse and map back to that starting point. So we're really focusing on just getting a plausible realization with a plausible wind ramp rate. But it's not really the right formulation to think about getting instantaneous agreement and getting to one exact scenario. So yeah, I guess in regards to wind ramping, we get the right wind ramp rate. And in the climate data, there's not a ground truth necessarily to say, does this ramp occur, at the right point, or is it actually 10 minutes later? Let's see. There's a question for Ganesh. Has this approach been combined with the development/optimization of model-based controllers, which try to reduce fatigue of the turbine?
Thanks. So I'm not sure if you are referring to the unsteady aerodynamics approach or the inverse design approach, but I'm going to answer this with respect to both approaches. So the first up regarding the unsteady aerodynamics models, yes, that is a very potential extension of this method where we can integrate that into model-based controllers and try and see if we can reduce the fatigue of the turbine with more accurate prediction of the loads. As far as the inverse design technique is concerned, right now we are focused on the just the inverse design as far as steady state operating conditions are concerned. Potential extensions of this technique to include fatigue model-based controllers is certainly possible, although we'll have to figure out some of the details here.
Great. We had another question in the chat about can AI/ML be part of the ultimate optimization process? And I think, yes, absolutely, that is our goal and our vision. Some of what Ganesh mentioned about incorporating the invertible neural net into Wisdom, I mean, that is directly plugging the AI/ML model into some of NREL's design and optimization tools. And I think also Dylan showed some examples around optimizing yaw angles with his graph neural net surrogate model. So absolutely, including it in optimization is on the table. Looks like there's a question for Mike from Dries. Dries writes, would you be able to train machine learning models to extrapolate surface data up to the height of the ABL or higher, say up to 2 kilometers? Would this work for any parameter, wind speed, potential temperature, etc.?
Yeah, thanks, Dries. Good to see you here. It's a great question. I think in principle, yes. The challenge would be model strength at that height. I think the benefit of these hub height winds is there's still a strong connection to what's happening at the surface. As you get higher and higher up, I think that correlation decreases. And so I would expect that we probably could and get accurate results on average, whether it's wind speed or potential temperature. But I expect the error to be higher than what we see, say, at 200 meters.
Looks like actually, Mike, there's another question for you about, have you tried to use your wind extrapolation approach at different locations other than the training data set location?
Yeah, excellent point. And that's exactly what we did. So what I didn't mention is that machine learning, if you're going to compare it to a generalizable extrapolation model like the log law or power law, it's a bit unfair to do it at the same site because a machine learning model needs that data at hub height, say, in order to train. And so in both papers, what we do is we implement what's known as a round robin approach. So we'll train, say, at one site one LiDAR and then evaluate its performance at the different LiDARs up to 10 to 100 kilometers away. And when we do that, we still find for the onshore case that the machine learning model outperforms the general log and other models, but not to the same extent as if it was at the same site. Interestingly, though, offshore, when we do the round robin at two LiDARs that were, about 80 kilometers apart, there was almost no degradation in model performance, which speaks to the horizontal homogeneity of the offshore environment. And is pretty promising, in particular, if we have just a few scattered LiDARs where we could train models regionally in principle. And what we're looking at now is being able to apply that using satellite data across the entire region and essentially have an observational-based wind atlas trained only on a few LiDARs. But excellent point, yeah, it's unfair to train and then test a model at the same site.
Cool. Looks like we also had a question from Jason. Jason writes, machine learning is often great at data interpolation, but extrapolation of data to extreme events is critically important in design applications. Can you comment on how to address this challenge? Sure. I think, well, in all of our case studies here, this issue of interpolation versus extrapolation comes up. The way I think about it, at least in the context of the super resolution work, is that if you're interested in studying super resolving wind data that includes, say, a hurricane field, you better include hurricanes in your training data set. Otherwise, it's not going to know the right physics to inject. And I think Ganesh would say the similar thing about studying airfoils, that we need to be including a really comprehensive training data set covering a variety of airfoil shapes. As far as being able to extrapolate, maybe I'll actually jump to this one last slide about things that are next, because some of the most exciting research I think that's out there is on kind of hybrid approaches that are combining machine learning techniques with first principles. And so this can be things like adding PDE terms into machine learning loss functions, or as part of a differential equation, having a machine learning model as just one of the terms alongside other first principles physics terms in that differential equation. And I think those kinds of hybrid approaches really are the best ways to start doing extrapolation. If you have a strictly data-driven approach, then I think you're probably better off sticking to interpolation. I don't know if any of the other presenters want to chime in on this issue around interpolation versus extrapolation. Nope. Okay. All right. We'll keep going, and I think there's a few more questions that have popped up. Looks like there was one for me about, in addition to generating ground truth, can GANs be used for forecasting and prediction? Can GANs outperform physical models, for example, WRF? So I would say GANs can outperform WRF in terms of computational cost. We're able to, as I talked about with the computational cost being so asymmetric, running the superres to enhance a data set is much faster than trying to nest WRF inside the model and actually spin up and run WRF. I don't know that it would exceed WRF as far as physical performance, because we trained it on WRF, so it's going to just reflect the physics that are in WRF. And then can we use it for forecasting and prediction? Not in the formulation that we've implemented. Here, this is really about enhancing already created time series that are just at a coarser resolution. There are other formulations for GANs, though, that do look at time stepping and going forward in time. And I think in particular, some of the recurrent neural net structures and LSTMs that Ganesh talked about in his unsteady aerodynamics, those architectures are maybe more appropriate for forecasting problems. And then looks like another question for Mike. Can we also use prediction from simplified models as input features? Simplified models will have better extrapolation performance. So I guess
Yeah.
my question is, can you have inputs that aren't just atmospheric variables, but are actually outputs from other models?
I think you definitely could, and I think that's the advantage of a statistical model. Even if the input feature has bias, as long as that bias is systematic and known, then a machine learning model can account for that and correct for that. So that becomes particularly advantageous when we're talking about satellite-derived winds, which are extrapolated to 10 meters based on neutral conditions. So there's going to be error there. But as long as that error, again, is systematic, there's no reason why you can't use simplified models to build a better extrapolation model. If you contrast that with a physical-based model, if your 10-meter wind speed's wrong, then that's going to propagate up to your hub height. So again, just another advantage of these, the flexibility of statistical models.
So I know we're at the end of our time slot. So maybe I'll just leave with our contact information up here. If I missed your question or if we didn't have time to get to it, feel free to reach out to any of us. And this recording or this presentation will be recorded and that'll be made available. So you can certainly go back to that. Otherwise, I think, on behalf of all the speakers, thanks for joining and sticking around for so long. And we look forward to seeing you guys at the next seminar in this series. So with that, I'll wrap up the meeting. Take care, everybody.